Okay, let's unpack this. If you are responsible for keeping the lights on in the modern world, you have to answer a central, almost existential question. How do you plan a completely stable electrical grid when one of your biggest, fastest growing news sources is also your most inherently unpredictable one? I'm talking about solar energy.
It is the ultimate planning challenge. I mean, if you're dealing with a traditional power plant, a gas turbine, or a coal plant, you have storable fuel. That generator is highly controllable, it's dispatchable.
Right.
But solar cell generators, or SCGs, they're dependent entirely on the sun, and it's non-storable. This uncertainty, it just creates havoc for planners.
And the source material we dove into today addresses this head-on. It's a deep dive into a unified probabilistic simulation framework, which they call PR-SOLS. And the mission is huge, to quantitatively evaluate the contribution of solar, not just in terms of raw energy, but across the three crucial pillars of grid planning.
Reliability, economic feasibility, and co-reduction. That's right. We are really unpacking the shift from older, sort of deterministic energy planning, where you just assumed plants worked until they broke down, to what the authors call an era of probabilistic realism. You have to plan for what might happen, not just what should happen.
And to really get why this shift is so crucial for solar, we have to start with why conventional models simply fail when you try to apply them to a solar farm.
Well, the foundational issue is what we can call the binary trap. For generations, system planners used a simple two-state model for conventional units like thermal or nuclear plants.
Two-state meaning?
They were either operating or they were in a state of forced outage. That's it. Their reliability was boiled down to a single number, the forced outage rate, or FOR.
So it's a simple, storable, and dispatchable resource with known failure parameters. You have 100 generators, you just calculate the probability of those units being down based on their FOR.
Exactly. But solar, it just doesn't fit that mold. It depends on what's called stochastic solar radiation, or SR. The sun doesn't follow an on-off switch. It follows clouds, seasons, the day-night cycle, and this forces us to confront a more nuanced view of uncertainty.
This is where we get the first real aha moment for you, the learner. The sources differentiate between two fundamentally different types of uncertainty that planners must handle: aleatory and epistemic. Let's really drill into that difference.
So, aleatory uncertainty is often described as the inherent randomness of the universe. Think of it as the luck of the draw. When a conventional generator suddenly trips offline because of a mechanical failure, that's aleatory uncertainty. It's an unpredictable, spontaneous event.
It's the randomness you account for with statistical reliability, like that simple forced outage rate.
Precisely. But then you have epistemic uncertainty, and this arises from incomplete knowledge. It's the uncertainty that comes from not having a perfect crystal ball. When you're trying to forecast what the load will be tomorrow, or critically, when you're trying to forecast how many clouds will pass over your solar farm in the next hour, that's epistemic uncertainty.
So if a thermal plant breaks down, that's aleatory. If the sun doesn't shine as bright as you predicted, that's epistemic.
Yes. And the critical insight the source material delivers is that SCGs suffer far more strongly from that epistemic uncertainty than any conventional plant. A conventional plant's output is known. Solar's output is driven by external variables the planner can only model probabilistically. This is why the binary model is, well, it's useless for solar.
So we have to move beyond the on-off switch. We need to transition to a multi-state probabilistic model. So how do the researchers actually build that model? You can't just plug in sunshine and get reliable numbers.
No, it requires a synthesis of statistics and physics. First, you need a mathematical description of the stochastic input, the solar resource itself. And empirical analyses of real-world solar radiation confirm that it generally follows a beta distribution.
Okay, for those of us less fluent in advanced stats, what does the beta distribution capture here that a normal, bell curve wouldn't?
A standard normal curve assumes results cluster around an average. The beta distribution is much more flexible. It's often used for variables constrained between 0 and 1, or in this case, 0 sunlight and maximum sunlight. It allows the model to capture the natural skew and the high frequency of lower radiance.
And the paper notes a key characteristic of real-world SR data. There is a huge built-in probability of 0 sunlight, something like 0.5.
Exactly. That high probability of 0 captures the natural diurnal or day-night cycle. It's a very necessary component of realism. The specific parameters they cite from empirical data alpha equals 0.12, and beta equals 6 show just how skewed the data is, emphasizing that sunlight is frequently low or non-existent and rarely at its maximum potential.
Okay, so we have a solid statistically defined probability distribution for how intense the sunlight is. The next step is turning that input, measured in watts per square meter, into the actual megawatts of useful electricity.
Yeah.
How's that conversion modeled physically?
That's where the PV output characteristic curve comes in. The model takes the beta distributed solar irradiance, the probability density function, or PDF, and integrates it with the known physical properties of the PV cell. The generated power, KBV, is defined by a specific functional relationship to the irradiance, GVFs.
And are there standard thresholds they rely on for this conversion?
Yes, and this is crucial. The functional output is defined relative to two standard benchmarks. First, the standard maximum SR, GSTD, which is typically 1,000 watts per square meter, what we consider peak sunlight.
Okay.
Second, a threshold radiation value, 4Shi day, usually around 150 watts per square meter.
Why is that 150 watts per square meter threshold so important?
Well, below that threshold, the physical characteristics of the PV material mean the cell isn't generating usable power efficiently. The generated unit power, it changes behavior dramatically around that 150 mark. By integrating the variable resource input, the beta distribution, with this fixed physical output function, you create the multi-state behavior.
I see. So it's the synthesis that's so powerful. You've essentially moved the SEG from being a simple, unreliable on-off switch to a generator with a full, complex spectrum of probabilistic output levels. Much more realistic.
That is the core breakthrough. And once we have that detailed multi-state outage capacity probability function for solar, we can finally integrate it into the massive system planning tool, Great Ball.
So let's pivot to the PI-SOL framework. What is the fundamental mechanism that allows it to handle the uncertainty of all generators, conventional and solar, simultaneously?
The backbone is a classic approach called the Booth-Bellerio methodology, which operates within the effective load model, or ELM framework. This is pretty standard in probabilistic power system planning, specifically at what's called hierarchical level I.
And hierarchical level I. That means it focuses on generation adequacy while simplifying the transmission network, for now.
Exactly. It's a starting point.
The idea of the effective load model is quite elegant, but needs a little unpacking. If the generators are uncertain, why is the model focusing on the load?
That's the genius of it. Instead of continually trying to calculate the varying output of thousands of generators, the ELM mathematically transfers the stochastic behavior, the outage probabilities of all those units, and shifts that uncertainty over to the demand side.
Wait, so you're not saying the load itself is uncertain. You're saying the load plus the risk of generator failure is calculated together.
Exactly. This transfer process is called convolution. Think of the original predictable load curve, say the known peak demand at 6 p.m. Convolution takes the generator's outage capacity distribution, the multi-state probabilities for solar, the two-state probability for gas, and mathematically smears that risk across the entire load profile.
So the resulting output isn't just the load, it's the load plus the likelihood that you won't be able to serve that load because of generator failures.
Precisely. That resulting curve is the equivalent load duration curve, ELDC. The ELDC is the single probabilistic point of truth that incorporates all uncertainties across the entire system.
That makes perfect sense. Once you have that ELDC, you can run the full spectrum of quantitative metrics, which the paper calculates over a standard one-year horizon. Let's quickly define those three critical categories, starting with reliability.
Okay, reliability is quantified using two key metrics. First, LOLE, or loss of load expectation, measured in hours per year. It tells you the expected duration of time the system will be short on supply.
Hours per year.
Okay. Second, EENS, which is expected energy not served, measured in megawatt hours per year. That represents the actual volume of energy shortage.
And for economic viability. I mean, that's essential for any market decisions.
For that, we look at the probabilistic production cost, PC. This factors in the varying fuel costs of the thermal generators that are still running, adjusted for the stochastic nature of the whole system.
And finally, the environmental impact.
That's calculated as total co-Euros emissions. Since the framework only models the output of conventional thermal plants and assumes renewables are zero emission, the KO-Euro number is directly proportional to how much non-renewable energy the system was forced to rely on.
Now we get to the proof of concept. The researchers validated this PI-SOL framework using a detailed case study of the scaled Jeju Island power system in Korea. What did that scenario look like?
It was a very realistic model using actual 2007 load data. The generation side had 13 thermal generators, plus 2 big HVDC transmission links bringing in power from the mainland. And critically, they included 3 SEGs, 3 solar farms, all modeled using this new multi-state approach.
And they ran increasing solar penetration scenarios to see how this solar capacity would impact the grid's performance.
Yes, 4 scenarios in total. They started with a base case of 300 milliOW of SCG capacity and ramped up to case 3, representing a pretty robust 1,300 milliOW of solar.
Okay, let's get to the results. Let's look at reliability first. Did that huge influx of inherently variable power destabilize the system, as some traditional planners might fear?
Quite the opposite. The reliability significantly improved, which validates that if you model solar correctly, it dramatically enhances grid adequacy. As SCG capacity increased from 300 milliOW to 1,300 milliOW, the LOLE, that expected outage, time dropped steadily.
Give us the numbers on that drop.
LOLE fell from 0.85 hours per year in the base case down to just 0.71 hours per year in the high penetration case 3.
Wow.
And similarly, the EENS, the physical energy shortage, dropped from 30.8 milliwatts per year to 25.55 milliwatts per year.
That's a measurable, tangible increase in system adequacy just by adding solar, when that solar is modeled with this probabilistic realism. But the economics are often the sticking point. How did that change?
This is where it gets really interesting. The increased solar penetration led to a massive reduction in the stochastic production costs. In the base case, the probabilistic production cost was around 366 billion Korean won per year.
Okay.
By case 3, that cost had plummeted to 255 billion won.
Wait, that's over a 30% reduction in production costs. That's
Yeah.
huge. It underscores that solar isn't just green. When integrated properly, it's financially beneficial because it offsets expensive fuel.
Absolutely. And the environmental results simply mirrored that drop. Kote-Euro's emissions fell dramatically, from over 2.3 million tons per year in the base case to about 1.6 million tons per year in case 3. The framework confirms that accurate solar modeling is the key to simultaneously hitting all 3 planning targets: reliability, cost, and environment.
Beyond just confirming solar's overall positive contribution, the framework provided some highly actionable, practical planning insights. Let's look at the sensitivity analysis, starting with data resolution.
Right, this deals with the issue of imperfect data. The researchers tested the impact of the data step size, or SRX, which is the interval used to discretize the solar radiation PDF when you build a multi-state model.
So planners often have to create artificial versions of these when local measurement data is limited.
Exactly. So they were essentially asking, how finely do we need to slice the data to get an accurate model without, overloading the computer?
And what did they find?
They found that reliability, costs, and co-Euro benefits improved as the resolution increased, but, and this is the key, the benefits began to saturate beyond 100 watts per square meter.
So 100 watts per square meter is the point of diminishing returns. That's a powerful takeaway for you, the learner. If you're a planner with limited data, you now have an optimal benchmark 100 that balances accuracy and computational complexity.
It saves time, saves resources, while still capturing the critical differences in solar output.
Another fascinating nuance was the importance of geographical specificity. They compared results using local Jeju Island SR data against substituting data from a different location, Jeju.
What's fascinating here is that the annual average SR between the 2 locations was only slightly different. Jeju was 277.5 watts per square meter versus Jinju's 243.8. You might think that difference is negligible.
But the framework found that using Jeju's local data consistently resulted in superior model performance, lower LOLE, lower ENS, and lower costs across the board.
It underscores a crucial point. Even small differences in regional solar resource characteristics, specifically the distribution of that irradiance, are absolutely critical inputs. You can't just use national averages. Planning needs hyperlocal data.
One final practical metric they evaluated provides insight into market mechanisms. The effective load carrying capability, or ELCC. This quantifies a generator's capacity value, meaning how much additional load can you safely add to the system without causing a reliability problem.
For the Jeju model, they calculated this capacity credit. When adding 100 milliW of SCG capacity moving from one scenario to the next, that addition yielded an ELCC of 11.7 milliW.
So for every 100 milliW of solar they added, the system could confidently support an additional 11.7 mW of load while maintaining the same reliability standard. That translates to an 11.7% capacity credit.
That is a highly valuable, tangible number for investment decisions. It shows how much utility an investor is actually getting in terms of grid stability when they build a new solar farm.
This PA-SOL framework really does accomplish its mission. It successfully integrates the traditionally separated evaluations, reliability, economics, environmental impact into a single, comprehensive structure, all based on that equivalent load duration curve concept.
And that unified framework is the central contribution. It's a huge step forward in planning realism. Now, it is important to remember that this current analysis was conducted at hierarchical level 1, or HLI.
Which, as you said, simplifies the assessment by neglecting transmission constraints, meaning they looked at whether there was enough power in total, but not whether the power could actually get from the generator to the specific demand center.
Exactly. The authors are clear that future research must extend this to hierarchical level 2, or HLII, which will incorporate transmission topology and operational constraints for an even more dynamic and realistic system assessment.
Which will be essential as solar generation sites are often remotely located. The study demonstrated all these results by using a standard industry reliability criterion, a loss of load expectation of 1.5 hours per year as a benchmark.
Right, that LOLE target is very common for long-term planning across utilities globally.
So here's the thought for you to carry forward to learner. We now have sophisticated tools like PA-SOL that can accurately model the highly variable nature of solar power. As solar penetration continues its rapid, unavoidable growth, the question for power system planners isn't just if solar helps meet reliability goals, but rather, how must those existing reliability standards themselves evolve to fully reflect and leverage the stochastic and intermittent nature of these indispensable renewable resources? It's not just about meeting the old planning criteria, it's about defining the new ones.